We're going to do two topics, areas and arc lengths. So it's just a review of everything we have been doing. And I'm probably one day going to switch this and do arc lengths first, just because I like arc lengths better than I like areas. But for now, let's go ahead and just do areas first. So section 10.4, areas and lengths in polar coordinates. That'll be today and Friday. And then we're done. Given a polar function, r equals f of theta, the area between the pole and the function is given by this formula right here. Now, if that seems somewhat familiar to you, it should. This is from your trig class and your pre-calculus course, but I'll go ahead and showcase it anyhow and give you a really strong justification, something you'll easily remember for future classes. So you have this full circle here, and I often forget to plot the center of it, and I need that. Okay, there we go. And you want to, let's just pretend, you want to find the area of a sector of that circle. So let's say you want to find the area of, let's say this sector right here. There we go. And it carves out an angle of theta. And again, it's a circle of radius r. If you want to know what this area here is, you just say to, or think to yourself, well, I have a circle and I know the area of a circle, but I don't have the entire circle. I only have a portion of the circle. We know the area of the entire circle is pi r squared, but we are only considering theta out of 2 pi of that. That's the portion of the circle we're looking at, right? If I were looking at 2 pi out of 2 pi of that, then I'd be looking at the full one circle. But right now, I'm only looking at a portion that is theta out of 2 pi of that entire circle. So the area is that portion of the full area. That is theta over 2 pi times pi r squared. That is, pi's cancel, 1/2 r squared theta. That is the area of a sector. Now imagine that I give you a polar curve. Here's the pole. Here's the polar axis. Polar curves are kind of neat because they swoop around like this. Okay. And you want to find, let's just pretend, the area of a big old sector of this. Let's just say you want to find that entire chunk right there. Well, what you can do if you want this entire chunk, maybe I'll highlight it so I can actually show you what I'm talking about. If you want the area of that entire chunk, as you turn from angle alpha to angle beta, what you're going to do is all your calculus you've done so far. You're going to slice it into n subintervals. However, the intervals are weird looking. They look like this. Let me get my ruler out. The intervals you're going to slice it into are emanating from the pole. That's one slice of it. It's like you're slicing up a pizza in a way. That's a good way to think about it. You're slicing up a pizza. And you want to find this area, and you basically want to add up all those little areas. Area sub ith. That's the ith area. Well, when looked at locally, this, if you disregard the black ink and just look at the red ink, this can be approximated by using the area of the circle that's a portion of, where this is some radius at the ith moment. And if that's true, I happen to know that area is just 1/2 that radius squared times whatever wiggle in theta that I have. Let me use a different ink for that. That's a wiggle in theta. And if you add up all those slices, you could see it'll be 1/2 r squared d theta. There you go. That is the proof of it. It's not much to it. So finding areas of polar regions is actually entertaining in some ways. It's not too terribly hard because you get to square things. Remember, when we were using arc length, we were taking square roots. And when you take square roots of things, stuff gets very ugly. But when you square things, actually, things go kind of nicely. So polar areas lead to easier integrals. However, conceptually, they tend to baffle people sometimes. The idea is really very nice. As long as you can remember the area of a sector formula, then you can remember the area of a polar region formula. You're just integrating that area of a sector over and over again. All right, so let's actually see it in action. Find the area of the shaded region under r is equal to square root of theta from theta equals 0 to 2 pi. Well, you don't see a shaded region, I hope, unless you can imagine one. I suppose it'd be very easy to imagine one. So I'm going to go ahead and draw in the pole. Let me use a different ink for that. There's the pole right there. And I'll draw in the polar axis. And here's where the art of graphing polars comes into play. I'm going to face an angle of 0. So I'm starting at angle 0. I'm going to face an angle of 0. So I'm going to face this direction. And I'm going to plot the point, or I'm going to throw a rock, let's just say, the square root of 0 units away from me, which is 0 units away from me. So basically, I drop a rock at my feet. It's me just dropping a rock at my feet when I'm facing this direction. However, as I increase the angle, so let's say we increase the angle to pi over 2. Let's just pretend. Well, then how far am I throwing a rock in front of me? The square root of pi over 2, whatever that distance is. But the idea is that as you're turning, you're throwing rocks further and further away from you. If I go to the angle pi, I'm throwing a rock. This is actually not going to work well if I leave it like that. If I turn through the angle pi, I'm throwing a rock square root of pi units in front of me. If I go to the angle 3 pi over 2, I'm throwing a rock square root of 3 pi over 2 in front of me. If I turn through an angle of 2 pi, I'm throwing a rock a distance of square root of 2 pi in front of me. So this, what I would call conch shell, is probably a pretty decent approximation of what r equals the square root of theta looks like. You could also go to Desmos and graph it. It pretty much looks like this. And you want to find the area of this curve, starting at the angle 0 and wrapping all the way around. You want to find this area right here. So let's go ahead and compute it. Computing the area here is super duper nice, because the area is just the integral from theta equals, we started at angle 0, to theta equals, we ended at the angle 2 pi, of 1/2 r squared d theta. What was r, though? Oh, r was the square root of theta. So this is going to be 1/2 integral from 0 to 2 pi of the square root of theta squared, or in other words, theta, d theta. Well, that's just going to be 1/2 theta squared over 2, evaluated from 0 to 2 pi. And that's going to be 1/4 times 4 pi squared. And that's going to be pi squared. Really nice, clean integral. super, super fast. So this is a great way to end the course, getting to these types of integrals that are actually somewhat fast. Not a fancy, crazy formula, just really nice, clean formula. The hardest thing that the hardest thing that students have with this is graphing. Let me just be honest with you. Again, I told you my expectations of what I expect you to be able to graph. R is equal to A plus or minus B sine or cosine of theta. And R is equal to A sine of theta or cosine of theta. However, every once in a while, you're given something like this, R is equal to square root, that you could easily just carve out like I just did. I just plugged in some points and found the pattern. That's really a very nice way to do it. So some of them, especially if R is just like not with sines or cosines, but just R is equal to some function of theta, sometimes that's easy to graph out. Sometimes it's not, though. So polars are difficult in that it's hard to know when it's going to be hard to graph and when it's going to be easy. Find the area of the region enclosed by the inner loop of this curve. Now, without me going through all the graphing goriness, I know that this is going to look like this. And you might say, how the heck did he know that so quickly? The reason why I knew that is because, and so let me hop back here and I'm going to show you something from our previous section we were just in. When we graph this gory detailed one, notice it has a very similar form. It's not 6 plus 12 sine of theta, but it's 3 plus 8 sine of theta. Notice it's a positive sine of theta. Let me say that again. Notice it's a positive sine of theta. Sine is associated with y values. And so this, to me, I always think of it this way. This, to me, is going to be a polar curve that's y value heavy on the positive y axis. Look at my red curve right here. It is actually y value heavy. Oh, I think something just died on my end. Hold on. Either my computer or my pen. Nope, that'd be my computer. Okay, it's back. I don't know what just happened. All right. So it is positive y heavy. That is, most of the curve is in the positive y direction. And that's the trick to this kind right here, is that they will be, if it's a positive sign, it'll be positive y heavy. If it's a negative sign, it'll be a negative y heavy. It'll be more like this. If it was a positive cosine, which deals with x values, it'll be positive x heavy. You can see, at least I can, that my computer's doing something weird on my end. If it's a negative x value, it'll be negative x heavy. I'm going to hop out of this screen because there's something up with something's happening on my end. So I'm going to hop over. Maybe I'll grab my other pen and hopefully that works better. All right. So I happen to know that because it's a positive sign here, it'll be y heavy. Now, how do I know that it has an inner loop? That's from experience, having graphed these so many times through the years. And this is still a terrible graph, to be honest with you. Let me get a good... That's a little bit better. All right. How do I know that it's a limit with an inner loop? That's from experience, but you can also just plot points very, very quickly. You can make a little table if you need to. Theta versus r. Theta being 0, then pi over 2, then pi, then 3 pi over 2. When theta is 0, you get 6 plus 0 or 6. When theta is pi over 2, you get 6 plus 12, which is 18. When theta is pi, you get 6 plus 0, which is 6. And when theta is 3 pi over 2, you get 6 minus 12, which is negative 6. Now, I'm going to use this color coding. I'm going to use black for this point. red for this point, green for this point, and blue for this point, just to showcase what they look like. So I'm facing an angle of 0, and I'm going to throw a rock 6 feet in front of me. Then I'm going to face an angle of pi over 2, and I'm going to throw a rock 18 feet in front of me. Then I'm going to face an angle of pi and throw a rock 6 feet in front of me. And finally, I'm going to face an angle of 3 pi over 2, but I'm throwing a rock 6 feet behind me. That is how I know what this curve looks like, that it has an inner loop that quickly. It's just because I can visualize very quickly the fact that I'm throwing rocks behind me at some point. Anyhow, we want to know the area of the region enclosed by this inner loop. Let me highlight the area that we want. We want to find that area right there. So essentially, we have a goal. Find this area. Our job is to find when do we start entering that area and when do we exit that area. And you could use symmetry here, but it's just easier just to say when do we enter and exit. So need to know when, that's theta, we enter the loop. And you could either say when we leave the loop, or you could say when we get halfway through the loop. And actually, we do know when we get halfway through the loop. So I'm okay with that. So, and when we either leave the loop or get halfway through. If you compute the area only to getting halfway through, that is, you will have found this area right here, you're going to double it up. That's the area of the full loop. If you just find out when you enter and leave, then integrate that. You've found the area of the full loop. But we happen to know that that right there, that point, happened when we were facing an angle of 3 pi over 2. So I happen to know when we're halfway through that loop. Let's find out when we enter the loop. We enter the loop when we're dropping a rock at our feet, basically. Or in other words, when r is 0. So all we need to do is find out when is that polar curve equal to 0? When is the radius or the distance we throw the rock 0? So we're going to solve 0 is equal to 6 plus 12 sine theta. That is negative 1/2 is equal to sine of theta. We know that the reference angle is pi over 6, and we know that sine is negative in quadrants 3 and 4. So our true angles are 7 pi over 6 and 11 pi over 6. So that's when we actually enter and exit. So I could just integrate from 7 pi over 6 to 11 pi over 6 if I want to. Or I can integrate from 7 pi over 6 to 3 pi over 2 and double it up. Doesn't really matter. It'll give you the same value. Hope that makes sense. There's a little spinning wheel on my end, so I'm very curious what that means. All right. This implies the area of the inner loop. I'm going to go ahead and just integrate from theta equals 7 pi over 6 to 3 pi over 2. And I'll double up that integral. You're more than welcome to go to 11 pi over 6. You can totally do that if you want. The 1/2 and the 2 will cancel. r squared. Let's see what r is. R is 6 plus 12 sine of theta. If you square that out, you'll get 36 plus, what did I say? 6 6 plus 12 is 72 times 2 is 144. So 144 sine theta plus, another 144 sine squared of theta, d theta. That is r squared right there. You can actually integrate each of those pieces very quickly. This will be 36 theta evaluated from 7 pi over 6 to 3 pi over 2 plus 144 times the antiderivative of the sine, which is actually a negative cosine, and plus 144. We know that the sine squared you can't integrate directly, so you have to use a half angle identity here. So we'll have 144 times the integral 7 pi over 6 to 3 pi over 2. Half angle identity is 1 minus cosine of the double angle, all divided by 2 d theta. And then you could finish this out. I'm sure that this is not going to be anything great. You can totally finish this out. I'm not going to bother with it, but ... So that's a very good example of the complexity that you sometimes face when you're dealing with polar curves. I'm going to take a drink real quick. All right, there we go. So that's the complexities that you'll face with areas of underneath polar curves. Sometimes it actually is incredibly beneficial to draw them if they're easy to draw. This type should be somewhat easy to draw. If you practice a few of them, you'll figure out they all kind of have the same shape in a way. So let's go ahead and sneak in another example. That way Friday is not such a packed day. What if we're asked to find the area of this region right here? So you can tell I snippet this out. So I have an outer function, g of theta. That's what the red curve is. And I have an inner function, this blue curve, which is f of theta. Well, the idea is exactly how it would be early in this course, in section 6.1, in fact, the very first section we had in this course. It's just, well, in that time, it was top minus bottom. And here it's furthest away minus closest. Farthest minus closest is a good way to think about it. And so if you do that, so if you find the area, let me just do it this way. Area should equal, well, we would integrate from alpha to beta, those are the angles, of the outer, which is 1/2 g of theta squared d theta. So that would give me all of this region right here. But then I want to subtract off the area underneath the function f. So I want to subtract off the integral from alpha to beta of 1/2 f squared of theta d theta. So I want to erase all that. And if I did that, I'd just be left with this highlighted area in, well, it was green, but I'm highlighting it. Now it just looks terrible. It looks like, I don't know what that looks like, honestly. But when you do that, you get the following. This is equal to 1/2 the integral from alpha to beta of g squared of theta minus f squared of theta d theta. And having written that and proven that, I could see there must be an error in my lecture notes, because that is not correct down here. It should be a 1/2 right here. So there you go. It's 1/2 radius outer squared minus radius inner squared. You have seen that notation before, right? The radius outer squared minus radius inner squared. So there you go. Same idea that we've done the entire course. Very, very nice. So this is really a great idea. And I've actually just proven it, by the way, but really, really great way of doing integrals, or at least finding areas underneath polar curves. There's nothing that should blow your mind at this point. So we'll finish out today's lecture with one final example. Area between two curves involves two curves where I told you earlier, I expect you to know how to graph these with some practice, obviously. So let's go ahead and find the area of the region that lies inside the first curve. So inside this, but outside the second curve. So we have to graph both of these curves. Now, something you might not know about this style of polar curve, 15 cosine of theta, that is just a circle heavy on the positive x axis. So this goes back to how I think about polar curves. When it's a cosine, I know it's going to be something like an x-axis curve. And if it's positive, I know it's on the positive x-axis. So I'm going to graph it, but then I'm going to justify it as well. So let's go ahead and I'm going to make the graph somewhat largish. So there's my pole right there. And actually 1, 2, 3. Eesh. 1, 2, 3. Okay. I just want to be as precise with this as possible. So that 15 cosine of x will actually, when graphed, look like this. It's actually a circle. I mean, a literal circle. It doesn't have radius 15. It has diameter 15. It has radius 7.5, actually. So that's kind of an interesting little bit. If you don't believe me about that, actually, let me turn off my ruler. I don't need it. If you don't believe me about that, build a table really quickly just for that first curve. Theta versus r. When theta is 0, we get 15 times the cosine of 0, which is 15. When theta is pi over 2, we get 15 times cosine of pi over 2, which is 0. All of a sudden, we're right here. 15 comma pi over 2. So somehow we got from this point, 15 comma 0, to this point, 15 pi over 2. Which way do we go? Well, if you think about the cosine curve, you could plug in something in between 0 and pi over 2 if you want, just to double check. So I will. If you plug in pi over 4, so you're facing an angle. My handwriting is just total crap these days. You plug in an angle of pi over 4, so you're facing 45 degrees, you're facing this direction. And 15 times that cosine of pi over 4 will be 15 over root 2. So you're throwing a rock, even though you're facing an angle of pi over 4, 45 degrees. Let me just show this. So you're facing that angle right there. You're throwing a rock in front of you. There we go, right to there. 15 over root 2 units. So this is 15 over root 2, comma pi over 4. Very fast way to graph this, but it's better to just know that. So we know, by the way, that it's carving it out this way. It's better just to know that when you have a times cosine of theta or a times sine of theta, those are circles. And if it's a cosine, it's a circle on the x-axis. If it's a sine, it's a circle on the y-axis. If it's positive cosine, it's on the positive x-axis. If it's a negative 15 cosine, it's on the negative x-axis. If it's a positive sign, it's on the positive y-axis. If it's a negative sign, it's on the negative y-axis. Another thing you'll need to know here is that when it carves out the circle, notice it carved out half the circle from time 0 to time pi over 2. That means it carves out the full circle in time pi. Kind of an interesting little side note there. Now let's go ahead and make a table for this guy right here. The fact that it says cosine, positive cosine, I know it's going to be positive x-axis heavy. Why is the leftmost point at theta equals pi over 2? Because if I'm facing an angle of pi over 2, what's cosine of pi over 2? Yeah, it's 0. So by the time we're facing due north, basically, we've dropped a rock at our feet. Our radius is 0. This goes twice as fast as most other graphs. It's a trip. Like, a lot of people don't realize that, but it does. That's why building a table is super nice, because you can see when does it land at my feet. So I think building a table like this is very powerful. I only needed actually half the table to find out what the full graph of cosine, 15 times a cosine, looks like. And now I move over. Yeah, not a problem. Now I move over to 7 plus the cosine of theta, and I'll do the same thing. I'll build a little table over here. Thetas versus r's. Now, again, I want to say this is a positive cosine, so it's going to be heavy on the positive x direction. Now let's start plugging in values. When theta is 0, cosine of 0 is 1, so the radius is 8. I will actually plot that. When the radius is pi over 2, sorry, when the angle is pi over 2. When the angle is pi over 2, so I'm facing due north, cosine of pi over 2 is 0, that'd be 7. So I'm going to go up 7 units when I'm facing due north. This is a lot different from that circle, which when you were facing due north, you just dropped a rock at your feet. This one, when I face due north, I'm going to go ahead and go forward. 1, 2, 3, 4, 5, 6. Oh, darn it. 1, 2, 3. How did I measure these out? Make sure I measured by doubles. Yes, I did. Okay. 1, 2, 3, 4, 5, 6, and 7. Right there. So I know I've gone from this point right here, and it's carved out. Now it won't be circular, so it's going to be a little bit like this. It's going to do something like that. It will have done something like that. That's the path it's been going. Now let's go ahead and try another value here. Let's say I'm facing an angle of pi. When I face an angle of pi, cosine of pi is -1. 7 minus 1 is 6. And this is an oddball, because this tells me that when I'm facing an angle of pi, this direction over here, I don't drop a rock at my feet. I don't drop a rock behind me. I still am throwing rocks in front of me, 6 feet in front of me. So let me plot a point. Come on. There we go. All right. Let me plot a point 6 feet in front of me when I'm facing the angle of pi. 1, 2, 3, 4, 5, and 6. Right there. So maybe my curve would look more like that, go through there like that. Let's erase that out. Oops. Darn it. Butterfingers today. It kind of flattens out, to be honest with you, right there, but I don't know anybody who requires that level of detail. So, and then as I turn past the angle of pi and put in 3 pi over 2, cosine of 3 pi over 2 is 0. So when I'm facing an angle of 3 pi over 2, which is straight down, I'm throwing a rock 7 feet in front of me. 1, 2, 3, 4, 5, 6, 7. There we go. I'm done with that ruler. Boom. Just looking at least somewhat symmetric. And it is all most, I shouldn't say all, but pretty much most polar curves are symmetric. So I'm just going to do this. There we go. Now, that was just a setup. We're knocking up against the clock here, but I do want to at least highlight and do a few things here. So we want to shade inside the circle and not include anything in that green circle. So I basically want everything inside of this circle, but still outside of that green curve. So I want all of this area right here. There we go. You can see it's symmetric. So what I could do is I could start by saying, okay, I want from angle 0. Oops, that's supposed to be theta equals 0. All the way to when they meet. So when I build this integral, which I will next class, but the area is going to be 1/2 the integral of, I'll start at an angle of 0, 0, and go to the angle where they meet. I will take the outer function and square it. The outer function is the 15 cosine of theta, so I'll square that. And subtract off the inner function squared, 7 plus cosine. And by the way, since we're going only half of this from 0 to basically we're finding this area right here, we'll want to double that up. So I'm going to put 2 here, doubled. There you go. And we'll finish it out next time because I'm a minute over, but there we go. We're actually very close to finishing the course. But these are kind of cool problems. You can actually start a lot of the problems in the 10-3, 10-4. Well, you could totally do all the 10-3. And then you can do a lot of the problems in the 10-4 homework as well. Just not the arc length ones. But all right. So I'll be back in about 9 minutes to start into office hours. You guys have a wonderful day. I'm still grading your exams, just letting you know. There's no quiz today. Again, just letting you know. Yeah, that's it. All right. I will see you either in office hours or I'll see you next time. You guys take care. Have a wonderful day.